All right, guys, welcome to another episode of Cuda Education. This is the compute cloth algorithm that I want to just quickly browse through on the surface level. I like to call this algorithm synchronization hell, but it's called compute cloth. A lot of synchronization is going on, a lot of things that, we're going to have to investigate. So this one's going to take some time. I'm going to do multiple videos on it. I'm going to repeat myself a lot. And, we're just going to go through, we're going to go through this algorithm multiple times because it's very important to understand what's going on with synchronization. I like to call this algorithm synchronization hell, right? It is one of the best algorithms, I think, just from a visual perspective, because you could see here, right, we have a ball and basically there's a cloth that goes around it and a canvas that goes around it. We see the ball and basically that's it. And we have a simulation of wind. So when we have a simulation of wind, you could see that like now the canvas is moving, right? The cloth is moving. All right, so that's pretty much it. If we turn off the wind, then things go back to what it was before, okay? Without any wind. And then if we turn on back the wind, we see the wind again. You see what I'm saying? So this is a compute cloth. All right. And that's what it's about. So first of all, guys, tutorial number 1 and tutorial number 13, if you want to install the Vulkan API on a Windows-based machine with a Vulkan-capable GPU. If you want to do the ray tracing examples, this example specifically is not ray tracing. So if you don't have a ray tracing capable GPU, it's fine for this example. But if you want to run the ray tracing examples, which I've done many videos on, which is these guys down here, the ray tracing stuff, you're gonna have to make sure you also have a ray tracing capable. For NVIDIA, it's RTX and above. I don't know about the other vendors, AMD and Intel. Okay, but yeah, this is just a quick run through of all that's going on in the algorithm. We're gonna have to spend a lot of time on it. I'm gonna do multiple videos. I'm gonna repeat myself to the point of annoying you, but it's important for us to really dive into the algorithm and understand. I think it's, as I said, it's one of the I think it's one of the the best algorithms in the example set, just because of the visual aspect of it and all that's going on. So yeah, as I learn, you guys learn also, and we learn together. Okay, so I don't pretend to be a Vulkan expert or a computer graphics expert. I'm just a guy trying to figure this out, just like you are. All right, so let's just dive into it. So a compute shader, Vulkan example, compute shader cloth simulation. A compute shader updates a shader stage storage buffer that contains particles held together by springs and also does basic collision detection against a sphere. This storage buffer is then used as a vertex input for the graphics part of the sample. All right, so basically, as you can see, it's a canvas that's falling on a sphere, right? And the big thing about all that's going on in this algorithm is that there's compute things going on and there's graphics things going on, right? You need to compute, the gravity, the simulation of the canvas or the cloth, hitting the sphere. How does the cloth change with when you hit the sphere? Wind. All of that stuff. There's compute stuff and there's graphics stuff, right? And you have to do this stuff in an organized fashion. Now, when you're dealing with computers, one thing that you have to to be mindful of is just memory, right? So, there's memory. The computer has memory. You know, you might compute stuff and store it in memory. You might read stuff from memory, and then you might display stuff, right? That's coming kind of from memory too. So there's like memory stuff. There's sort of a storage buffer stuff, and there's compute stuff, and there's graphics stuff, right? So the big thing about this algorithm is that, like, there's like pipeline barriers and there's like semaphores, okay? There's pipeline barriers, which, just make sure like one thing happens before the other in the pipeline. There's semaphores, which, just make sure on the GPU side that when you have two processes on the GPU, one process happens before the other process starts, right? This is all stuff that I'm gonna have to dive into, right? And the code is this is the updated code, so the 2025 version of the code on GitHub, right? This code is freely available for all to investigate, right? But there's command buffer stuff, so it's a lot of things are colliding in this algorithm, right? And we sort of have to sort it out in a way that we could understand it, right? Just the way how programming works and just how Vulkan works and trying to get stuff done. The way how it's displayed typographically on in the code, it's not necessarily very intuitive. Now it's no one's fault. It's no one's fault. It's just computer science, right? It's just the way how things are. It's a lot of moving parts, and it's not necessarily intuitive. But that's why Cuda education is here. We are here to make things simple, straightforward, and understandable for everyone that wants to learn. Okay, so bear with me as we go through all that's happening here. But yeah, there is pipeline barrier stuff. There's semaphore stuff, which is two processes on the GPU, and you need to make sure that one process happens before the other. The pipeline barrier stuff, one thing happens in the pipeline before the other. There is queue family stuff. So queue family is, for your particular implementation of Vulkan, do you have a dedicated compute queue? Do you have a dedicated graphics queue? Or is the compute and graphics combined in the same queue family? If it's combined in the same queue family, then we have to take a certain thread, a certain route through the code. If it's two separate queues, then we have to accommodate for that, right? So you have to switch ownership between the queues and stuff, right? So pipeline barrier stuff, semaphore stuff, queue family stuff, command buffer stuff. So are we doing things and we have to manage things inside of the same command buffer? There's like frame stuff. So is the previous frame completely finished before the next frame starts? Is all the compute for the previous frame done before we start on the next frame? There's compute and graphics stuff. So we're not going to display stuff before we finish computing what the hell we want to display, right? And once we finish displaying on the graphics side, we're not going to start compute until we know we're finished displaying on the graphics side, right? So, compute and graphics stuff, read and write stuff. So you're not going to read before you're finished writing to memory, and you're not going to write before you're finished reading what you need to read. What else? yeah, I said Q family ownership stuff. So this is a lot. It's a lot. It's a lot to get into. You know, as I said, I'm gonna make a lot of videos on it. Yeah, it's you know, but once we sort of fully tackle all of this stuff, we will be better for it, right? And we'll have a better grasp of we'll have a better grasp of we'll have a better grasp of Vulkan, right? Um, so yeah, it's important that you guys pay attention with these videos, right? Especially this one, right? Because it's just a lot. It's a lot. All right. So let's just go through it. Okay. So we have this will be set to true, dedicated compute queue. So remember we talked about compute queues, right? So some, depending on your implementation of Vulkan and your hardware capabilities, well, basically depending on your hardware capabilities, because not everyone has the same GPU, right? Not everyone has the same GPU. So if you have older GPU, you might have a dedicated compute queue family, right? Like compute is being done on a queue family that is dedicated to compute stuff, right? That's maybe on older hardware. On newer hardware, the compute and graphics queue, you know, it's the same queue family. Okay, don't want to dive too much into it, but just understand that depending on what hardware you're running on, that you know this is a consideration. So this flag right here, what this flag right here is saying is this will be set to true if the device has a dedicated queue for a compute only queue family. With such a queue, graphics and compute workloads can run in parallel, but this also requires additional barriers, often called async compute. These barriers will release and acquire the resources used in graphics and compute between the different queue families. So listen, maybe I switched it up. Maybe the newer hardware has dedicated, but I believe that the newer hardware has a combined, you know, compute and graphics are on the same queue, right? But just understand that this will be true if the device has a dedicated queue family for a queue only. With such a queue, graphics and compute workloads can be run with such. Yeah. Okay. So basically, you know, if you have dedicated compute and graphics queues, then you could do stuff in parallel, which means both things can be happening at the same time. You could be computing and like doing graphic stuff at the same time, right? But if it's, you know, so with such a queue, graphics and compute workloads can run in parallel, right? But this also requires additional barriers, often called async compute. These barriers will release and acquire the resources used in graphics and compute between the different queue families, right? So if you have dedicated, it's almost like if you have dedicated cubicles or dedicated pods, right? If you have dedicated like compute and graphics pods, right, then you have to transfer ownership between the two, right? You can't, you know, you can't, you have to put barriers in place to make sure that like when you're reading something or when you're doing something, it's not affecting the other side and stuff. So you need to make sure that there's synchronization done between the two pods or the two barriers, right? It says, right, they can work in parallel, but you have to manage the parallelism, right? They can work in parallel. These barriers will release and acquire the resources used in graphics and compute between the different queue families. So, you know, there's like memory resources. So you don't want the two of them, you know, you don't want one to be, you don't want the both of them to be working on the same piece of memory. You don't want to be reading while the other is writing to the same piece of memory, right? If you have the parallelism, but then you have to manage the synchronization between the two. That's all this is saying. So so that's what this flag is right here. Simulate wind is false. So basically, upon running the algorithm, we just assume we turn off the simulate wind. Okay. Read set and index count, we leave that alone for now. We have our texture cloth and we have our model sphere, okay? The cloth is made from a grid of particles, so we have all of these particles and stuff, right? No problem. All these attributes for the particle, position, velocity, normal, all of that, UV. Okay, cloth definition parameters, right? So the size of the cloth and all of that stuff. I play around with this stuff, but I'll do that in a later video. We put resource types into struts to make this sample easier to understand, okay? Well, thank you. We use two buffers for our cloth simulation, one with the input cloth data and one for outputting updated values. We use two buffers, right? The compute pipeline will update the output buffer. The graphics pipeline will use it as a vertex buffer, okay? So here we have another distinction. We have input stuff and output stuff. Right, so we input like the cloth data and then we output updated values. Now these updated values have gone through a certain process in order for them to be quote unquote updated, right? But again, we have to manage this stuff, right? There's no such thing as a free lunch in Vulkan. There's no such thing, never. Everything has to be explicitly managed. No such thing as a free lunch. I don't care how many extensions they want to release, okay? I don't care how cute they think they are. There is no free lunch in Vulkan. Everything has to be managed. So we have a strut of input and output stuff. Okay, we'll leave that alone for now. Let's move on. Okay, resources for the graphics part of the example. And we have a whole bunch of resources for the graphics part. Okay. VK pipeline cloth, VK pipeline sphere. Pipelines, okay? The vertices will be stored in a shader, storage buffer, so we only need an index buffer in this structure. Okay, I'll leave that alone for now. We're leaving stuff alone. We'll get back to it, I guess, at a later video, okay? Resource for the compute part of the example. Number of compute buffers set to 1 for serialized processing or 2 for in parallel with graphics queue. Okay. Number of compute command buffers. Set 1 for serialized processing. So just as a simple thing, you know, if you just have one buffer, then you don't have, you can only really do one thing at a time. But if you have two, then you could do stuff in parallel. All right. So let's just focus on this little piece right here. So you guys know what a semaphore is. I've done many videos talking about semaphores. I actually have a whiteboard talking about semaphores. You guys know what semaphores are. If you're new to the channel, if you're new to the team, if you're new to the dream, semaphores are things that they're synchronization tools that live on the GPU. They're synchronization tools that live on the GPU. GPU only, okay? There's CPU and there's GPU. GPU only. So the semaphore, semaphores basically make sure that one process it flags, right? It flags, and it makes sure that one process is done before the next process starts on the GPU, right? So it's a flag kind of thing, right? So I start a process, I finish a process, like say process 1, and then And then the semaphore would say, okay, this process is complete. The next process 2 says, okay, can I start my process, right? If the semaphore flags that it's not complete, then you can't start process 2. Okay, that's just my simple version of the semaphore stuff. Again, semaphores only deal with GPU stuff. Another thing, as of my last investigation of semaphores, is this. You don't explicitly know You don't explicitly know, like, it's not something that you could readily query or control. You basically, you set up rules and you submit those rules with the semaphores in baked into your whole workload, and then all you could really know is that the rules have been, adhered to, right? You don't necessarily, you can't directly, as of my whiteboard edition and the last time I investigated this stuff, you can't really necessarily query all the time, um, from you as a programmer or developer on like you can't really query the state of the semaphores. All you could do is like submit a workload or submit a process, a big process, and say, okay, these are the semaphores you're working with, and blah blah blah. These are the rules. Process 2 can't start until process 1 is done. Um, you know, process 1 turns off the semaphore, and then or puts it as complete. While it's doing its work, it flags the semaphores and stuff, but you can't really query the state of the semaphore. You just put the workload on the GPU, and you put these rules in place, and you just press go, and you could just be fairly confident that the rules have been followed, right? But you can't really, as of the last time I investigated this stuff. Maybe they updated Vulkan. Maybe they did some extension stuff. I don't know. I'm not gonna. Right. So anyway, so we have our ready and our complete. Right. So semaphore stuff. Right. Um, More semaphore stuff. Right here. We'll investigate further. Now we have our fences. Right. Fences. Okay, so fences. Now I did a whiteboard in the same video. I did a whiteboard on the fence stuff. Now the fence stuff is CPU and GPU synchronization. So the CPU submits something to the GPU. If the GPU so the CPU submits stuff to the GPU, the CPU then waits for signal from the GPU that the process is done. Once the process is done, then the CPU, if it wants to, can submit another process or a workload. Okay, that's what fences are. It's CPU to GPU synchronization. Now, with fences, the reason why you need them is because you don't want the CPU to be submitting workloads, like just stacking up workloads and keep submitting and submitting and submitting without any way for the CPU to know whether the previous workload is done, right? Just in my estimation, just me, it's very bad when you're submitting stuff to the GPU and you're overloading the GPU, and you have no idea whether your previous submissions have been completed. So what fences do is give the CPU clearance or validation or vetting to say, okay, my first workload submission was done. I can now submit my second workload submission to the GPU, right? You don't want to be submitting workload 1, 2, 3, 4, 5, 6, 7, a million, 1,000,001, 1,000,002, 2,000,000. You don't want to be just submitting stuff and you have no idea of whether the previous, workload 500,000 has been completed yet, right? Because then you overload the system. You might get, RAM issues. I don't know, memory leaks. I don't know. You're gonna crash your system because you're submitting all these workloads, and you have to remember that you're submitting these workloads too, and you have to manage all of that, and you have no idea of knowing whether the previous workload is done. And of course, being who we are, programmers and developers and stuff, sometimes you need process workload 1 to be done before you start workload 2, and workload 2 to be done before you start workload 3, right? So that's what fences are. Okay, queue, command pool, command buffers, right? All of this stuff we will get into at some point. These arguments define the spring setup for the cloth piece. Changing these values changes how the cloth reacts. You know, we'll mess around with this stuff at a, you know, in later videos. Yeah. Okay. Vulkan example base. Okay. Standard issue camera stuff. Deconstructor stuff. We have graphics stuff and we have compute stuff that we have to deconstruct. We have to destroy our fences. We have to destroy our semaphores, right? Fences, CPU to GPU synchronization. Semaphore, GPU to GPU synchronization. Two processes on the GPU. Command pool, blah, blah, blah. Input and output, okay? Right, so this enable physical device feature is required for this example. So like, you know, you have to basically profile the hardware that you're running on. Remember the author submit this stuff, you know, put this stuff on GitHub and all that stuff, but everybody's environment is different. So you need to make sure that your hardware capabilities that you're attempting to run this algorithm on is capable of doing the things that you need it to do in order to run the algorithm, right? Load assets, we load the sphere and we load the cloth, right? This is like, so we know sphere, GLTF, we did some stuff on GLTF, and this is like a texture stuff, which I haven't gone into, the .ktx file, you know, a lot of stuff going on here. Okay, add graphics to compute barrier. So this is where we get into the mix of things. Right, so this talks about transferring ownership of, you know, this talks about transferring ownership between, you know, the graphics and the compute barrier. So you're moving ownership from graphics to compute. Add graphics to compute barrier. Okay. This talks about the Q family stuff, right? Q family stuff, right? Q family. So we have a whole bunch of parameters that we have here. We're just looking at the signature of the function, right? If dedicated compute queue, right? So if you know, if the hardware has a dedicated compute queue, we do you know, stuff, okay? Just notice here that the source queue family is the graphics, and the destination queue family is compute. So we're basically transferring ownership. This is a cross queue function, right? Queue context, it's a cross queue function, okay? So we're moving from graphics to compute, okay? Let us not get too involved. We don't want to get our hands too dirty in this. Just notice that we also have this pipeline, VK-CMD pipeline barrier, okay? So there's like a pipeline constraint on it. This is a heavy synchronization barrier. Okay, so, you know, right, so it controls memory visibility and execution ordering, okay? It's a heavy barrier. So one stage happens, execution dependency. One stage happens before another stage starts, right? And one stage happens before another stage starts. That's these two parameters here, right? Which is, I guess, these two guys right here. Right, memory writes from the previous work are visible to later work, right? And that is right. So memory writes from previous work is I believe this part right here, but we will get into that. We'll get into it in more detail later. But just understand that this is a synchron. I mean, this is at the heart of why this function exists, right? So we're transferring ownership and all of that stuff, and okay, right. I guess it's collapsed into this thing right here, right? The buffer barriers, right? So, all of this is boilerplate and leading up to putting it into the VK-CMD pipeline barrier synchronization thing, okay? We shall get into it, but wanted to just do an initial thing, right? So VK-CMD pipeline barriers. And of course, guys, you know my rule. Anytime you see a lowercase VK function, you know that it's really important, right, for what we're trying to do. All right. So that's add graphics to compute barriers. Now, we have the opposite function, which is add compute to... Oh, no. That's not the opposite function. Let's just jump to... So add graphics to compute barrier. Let's just jump to add compute to graphics barrier. So this is the opposite function. I'm going to skip this one right here. Let's just do the opposite function. Now you're going to see the source queue family index for the add graphics to compute barriers. The source is the graphics and the destination is the compute, right? If we go to the compute to graphics barriers, add compute to graphics barriers, we're going to see that it's the opposite. The source is the compute and the destination is the graphics. So again, we're dealing with ownership stuff, and we are transferring from graphics to compute, right? And here we're transferring from compute to graphics, okay? We still have our VK-CMD pipeline barrier, but now the buffer barriers variable is built differently, right? Depending on the function, okay? So this is cross-queue shenanigans that we're doing. Cross-queue shenanigans, right? We're going from graphics to compute here, and we're going from compute to graphics here, all right? Let's not dive too much more deep into it. We still have our source and destination, but let's just leave that for notice that we're still checking for the dedicated compute queue, right? We're still checking for dedicated compute queue, okay? But let's just leave that for now. All right, now we have our add compute to compute barriers. Now this is not cross queue family ownership stuff. We're not managing, because they're both compute, they're both in the compute queue. Okay, but I believe with this one, we have to make sure that, like, I think it's a frame by frame thing, and we have to make sure that, like, the two things aren't the two frames aren't like trying to write or compute to the same piece of memory, right? It's something to do with the command buffer. Just give me a second here. Right, so we're not transferring ownership. Right, so the queue context is the same queue. So let's see what he has here. Right, we have written to the output buffer and need a memory barrier before reading it. Don't need a memory barrier for input buffer. The execution barrier is enough. Okay. If we said we have written to the input buffer and need a barrier before reading it, right? Don't need a memory buffer for the output barrier. The execution barrier is enough. Okay. Yeah, but basically, you know, from one compute to the next, whether it be from one frame to the next, it's compute write and compute read, right? But compute write and compute read. But you don't want to be reading if you haven't finished writing, and you don't want to be writing if you haven't finished reading, right? So you need a barrier, right? So compute wrote to SSBO. Make those writes visible to the next compute read on the same queue, right? So it's, you know, that's what this guy is. But notice it's different from graphics to compute barrier and compute to graphics barrier. Okay, let's just leave it at that for now, and you know, we'll not go further depth into this part right here. Set up and fill the shader storage buffers containing the particles. These buffers are used as shaders, storage buffers in the compute shader to update them, and as vertex input in the vertex shader to display them, right? So again, we're computing stuff and then we're displaying stuff, right? We'll leave this alone for now. All right, we have our favorite staging buffer. I did a whole video on the staging buffer, whiteboard even. But yeah, you want to copy it to the local device. So this is when it says device local memory, it's talking about the GPU memory. You want to basically SSBOs won't be changed on host after upload. So copy to device local memory, right? So, you know, we want to do things on the GPU, and we're only going to continue to update on the GPU, right? You guys are familiar with this buffer stuff. Host visible bit, host coherent bit, right? Not going to get into it too much right now. Create buffer, create buffer, create buffer. We have the input and we have the outputs. And we have this guy up here, which I guess is a staging, right? The staging buffer, which is like the intermediary, right? And then we're copying from the staging buffer. Right, add an additional release barrier to the graphics queue so that when the compute command buffer executes for the first time, it doesn't complain about a lack of a corresponding release to its acquire. I normally play around with this, and like, you know, I would play around with this and like basically lock it so that, like, you know, so that like the compute the compute never really gets to execute because it's waiting for the release of the previous computation. I normally, you know, would just run the example and do it, but for some reason, like, I have to be careful with running the examples, and I'm so deep into this video that I don't want to mess up the video at this point. But yeah, because I've been having, like, when I run the example, sometimes, you know, things get weird. But all right, sorry for this random rant. Okay, so you know, as I said, this algorithm is synchronization hell. Add an additional release barrier to the graphics queue so that when the compute command buffer executes for the first time, so we're talking about initial conditions. We're talking about initial conditions. For initial conditions, we wanna have the flag of release so that the compute can like start to do its thing. If the compute doesn't see release as basically like the barrier is released, it's gonna sit there and wait for that release barrier. Well, if you're doing stuff for the first time, there is no release barrier because the graphics queue hasn't run yet. So it's just going to sit there and wait, and it's never going to compute, and it's never going to update, and the cloth is just going to stay hanging over the sphere and never fall, right? So that's the context of this discussion right here. We for the very first initial condition, for the first time we're running it, we raise the release flag, and then we say add an initial release barrier to the graphics queue so that when the compute command buffer executes for the first time, it doesn't complain about a lack of a corresponding release to its acquire, right? So before it can acquire it, it's looking for the release. So, but for our very first time, we have to we have to sort of we have to sort of juice the thing or trick the algorithm to say, hey, here's your release that you're looking for. So for the very first time, you could do the compute. Now, once you do the compute, you've acquired and you've done the compute, then the compute is going to raise a release flag. Once the compute raises the release flag, then the graphics queue can acquire, the graphics can display the stuff that was computed, and then the graphics can do its release, and then the compute can do it again for the next frame. Okay, that's what this discussion is, right? And here in all of this, that's what this guy is. Add graphics to compute barrier, right? So again, we talked about moving ownership from one to the other, right? So we're releasing from graphics and we're giving ownership to compute, right? I'll do another video messing around with this so you guys can see. So like I think for me to like disable this release, I basically just comment this out for the very first time. I comment this command out, and then like the cloth will just hang over the sphere. But I might be, we'll investigate in another video. But that's what this guy is here. We have to juice the thing and like give it a release first, a dummy release, so that the compute can start and then the chain of command continues, right? And then we destroy the staging buffer. We have our indices and stuff. Staging buffer stuff. Copy from staging buffer, right? Okay, prepare descriptor pool. This is shared between the graphics and compute. Prepare the resources for the graphics part of the sample. Uniform buffers for passing data to the vertex shader. We will dive into this stuff later. Let's not get too involved at this point. There's certain things I wanted to highlight here. Not for now. Vertex shader, fragment shader. Prepare resources used for compute part of the sample. Don't really want to dive too much into this stuff right now. We have done descriptor set stuff, so you guys should be familiar with the descriptor set stuff. Did a whiteboard and everything on it. VK update descriptor sets. All right, so that's a whole nother discussion. Create command buffers for compute, fences to check for command buffer completion, right? So remember we talked about fences being CPU to GPU synchronization, right? So that's this guy right here. To check for a command buffer, right? So we're checking that the command buffer is complete. That's what this stuff is right here. Semaphores for graphics compute synchronization. Now, the thing with the graphics and the compute, this is all being done on the GPU, right? This is all being done on the GPU. The graphics and compute stuff is all being done on the GPU. So that's why we need a semaphore, right? And again, semaphore is GPU to GPU synchronization, two processes running on the GPU, and you need to have barriers to make sure one is complete before the other starts. So that's what this semaphore conversation is, right? I believe it's here. Okay, so maybe it's here where I do the I lock the signal first used ready semaphore, right? So signal semaphore count 1 ready, right? So I think it might have been, it's either here or up before, where I basically, you know, disable the ready semaphore so that you know, the cloth is like locked in place, right? And you can't compute the next frame because it's waiting for the ready semaphore, right? But you know, you guys understand the context of this. Signal first used ready semaphore. So we're basically telling the compute that, you know, it's ready, that the semaphore from the graphics is flagged as ready, so we could proceed with our compute stuff, right? I believe it might be here that I disable it. So either one of the two, but we'll investigate that in another video, okay? And then we submit the work, okay? Update compute UBO. Haven't played around with this. Update compute UBO. You know, maybe in another video I'll play around with this and see what happens. Clamp frame timer to max 20 ms, milliseconds refresh period. Otherwise, image breakup can occur. Okay. We have our simulate wind. Update compute UBO. So you guys know UBOs, are uniform buffer objects, are used to sort of manage data and like, you know, I believe this UBO stuff, it's like updated on the CPU side. So it's updated on the CPU side and then like transferred over to the GPU. But basically, we have to do a calculation to simulate the wind, right? So wind is not just wind, right? We don't have wind in our GPU, right? It's not a readily available thing in our GPU or in our CPU, right? It's wind is a calculated it's a calculated process, okay? So you know, you can't go to the weather channel and order a wind attachment for your computer hardware, right? Wind is calculated. It's a mathematical computation, right? And if you're so inclined, feel free to dive into the calculation here. I am not going to do that, but just understand that you know, to update the computations and affect the application, we do it through the uniform buffer object. You know, data type. Okay, I don't want to get too much into it, but just understand uniform buffer objects, right? And it's a computation that's done. And then if we don't want the wind, then we just set it here. Okay. Yeah, so I believe this memcopy function, it's a C++ or C# or whatever function. So I believe it's from CPU to GPU, okay? So that's that. Okay, update graphics UBO. So we have our compute function to update the compute stuff through the UBO. We also have a graphics thing. What are we updating for the graphics? Okay, so for the graphics, it's just we're updating the camera. Okay, and we do have our memcopy again. So I believe memcopy, as I said, is from CPU into GPU. Okay, but yeah, so we'll leave that alone for now. Prepare. Okay, we prepare. Load assets, load, prepare staging buffers, prepare descriptor pool, prepare graphics, prepare compute, prepared equals true. All right. Build graphics command buffer. Okay, build graphics command buffer. So build graphics command buffer. What do I want to highlight here? Okay, acquire storage buffers from compute queue. Acquire storage buffers from compute queue. Okay, acquire storage buffers from compute queue. What do we need for that? We need our little trusty function called add compute to graphics barriers. Okay, so this is transferring ownership, right? So we have the compute and we're moving to the graphics. So we're transferring ownership from compute into the graphics, right? Notice this is the build graphics command buffer. So we need to acquire ownership from compute into the graphics queue, right? So that's what this function is all about. Yeah. So it makes sense, right? We're not completely out of the water with this one. We know that we understand the meaning of this function, right? Draw the particle system using the update vertex buffer. So yeah, we will get into all of that another time. Release the storage buffers to the compute queue. Okay, so here we had our acquire storage buffers from the compute queue, and we're releasing the storage buffer to the compute queue. So if we're releasing to the compute queue, then we have to have a function called add graphics to compute barriers. So again, we're transferring ownership from one queue family to another, right? It all makes sense. Add graphics to compute barrier, right? We're releasing ownership from graphics and we're giving the compute, the ability to acquire, okay? It's a lot of stuff going on, a lot of separate processes happening. So, we'll have to organize ourselves. I probably have to do a whiteboard at some point to sort of make all this thing make sense. But I need to understand it first before I could do that. Okay, build compute command buffer. Build compute command buffer. Okay, so now we're building the compute command buffer. Acquire the storage buffers from the graphics queue. So what do? Add graphics to compute barrier, right? So we're acquiring from graphics, right? So here we were right. So here we were acquiring from compute. Here we're acquiring from graphics. So add graphics to compute barrier, right? Because now we're in the build a compute command buffer, right? And similarly, we are going to have to add compute. So release the storage buffers back to the graphics queue, right? So we're going to have to release and do. So we have add graphics to compute barrier, add compute to graphics barrier, okay? Here we had add compute to graphics barrier, add graphics to compute barrier, right? So you guys get the general flow of how this all works, right? We render we have our render function. We render, we render, we render. What I want to highlight here is that, okay, so wait for VK wait for fences, right? And then VK reset fences. Okay, so when we see fences, we automatically know, guys, once we see fences, we automatically know that we are dealing with CPU to GPU synchronization. That's all I want you to take from this right here. We're not gonna get into anything else. All we want to know is that we're dealing with CPU to GPU synchronization here. Submit compute commands, update compute UBOs, build compute command buffer, right? So update compute UBOs, we also know that that has to do with the mem copy stuff. So this has something to do with like CPU and GPU synchronization stuff too, right? Or like the, you know, CPU going to the GPU, right? Because we know we had that mem copy function. Let us leave this alone, except for we're talking about semaphores. So we're waiting for a semaphore signal 1, the signal count 1, and signal count signal count 1 and signal count right, we have our signal semaphore as complete. And right, so we're dealing with semaphore stuff, right? So remember I said the compute and the graphics is being done on the GPU, right? So if it's GPU to GPU stuff, we're in the semaphore land, right? And all of this stuff is dealing with semaphores. Q submit, but we also, so we have our VKQ submit. We do have our submit info, which deals with the semaphore stuff, but we also have our fences, which deals with CPU to GPU relationships. But we'll investigate this at another time. You see that the thing with just Vulkan and you know the algorithm and stuff is that, you know, there's a lot of things happening in sort of parallel, a lot of separate conversations that all come together to give us our application, right? So it's a lot of different worlds that we're trying to manage and deal with at the same time. And that's what kind of makes it difficult to really understand and put things into proper context, because it's just a lot of things happening at the same time, and we need to, you know, we need to understand the full picture so that we could, you know, we could make sense of all that's going on, right? But it's just a Vulkan thing. It's just a computer graphics thing. It's just a dealing with dealing with CPU and GPU stuff and GPU stuff. The GPU is very powerful. It has a lot of capability, but that also means that there's a lot of complexity going on. Okay, but trust that Cuda Education is here, and we will figure all this stuff out. But just understand, guys, that there's semaphore stuff and there's CPU to GPU stuff. So GPU to GPU stuff and CPU to GPU stuff. All right. Submit graphics commands. So we're going to submit graphics commands. I don't know why these two are commented out. We'll leave that alone. But we sort of have the same. We sort of have the same pattern here, or cadence, or flow, or vibration even. All right, so we have our semaphores, wait semaphore, signal semaphore, and we have more semaphore stuff. And we also do have our wait fences stuff. I'm not sure why this is commented out. I don't know if this. I know the author of this algorithm. He updated everything. You know, he updated these algorithms. So maybe this was from the old algorithm. I don't know. But yeah. Right. So we have semaphore and fences stuff, right? And then we have our overlay, or user interface overlay. But all right, guys, that is the conclusion of this video. I'm at an hour solid for this video, which is good timing. So as you can see, guys, a lot of stuff is going on with this algorithm. That's why I called it synchronization hell. But we have to go through it. We got to walk through hell. It's just how the game is played. We got to do it. I know it's hard. I know it's confusing. I'm going to have to make many videos. I'm going to have to repeat myself a million times so you guys understand. You got to understand, guys, I'm competing with TikTok. And you guys can't focus on something for more than a quarter of a second before you move to the next post. Okay? So, listen, I should win a Nobel Prize. I should win a Nobel Peace Prize. I should win a Nobel Prize for computer graphics. I should win a Nobel Prize for computer science. I don't know why, I don't know why I wasn't put up for consideration for this year. But next year, we're going to make a run for it. Right, guys? That's right. Next year, we are going to make a run to get a Nobel Prize. And the world will be a better place for it. All right, guys. Yeah, long video today. Long video again. If you guys want to run this stuff on your machine, you need to have a Windows machine with a Vulkan-capable GPU. And if you want to run the ray tracing stuff, this is not a ray tracing example, but if you want to run the ray tracing stuff, you need to have a ray tracing capable GPU. Tutorial number 1 installs the Vulkan API. And tutorial number 13 installs all of these examples on your machine. So definitely check it out, guys. Support the channel, like, subscribe, tell your friends about it. Work on this stuff. This is hard work. I'm not just creating flashy marketing videos that just show you cool stuff. I'm actually trying to show you guys how to do this stuff for yourself. And you can unleash your creativity on the world, right? For you guys doing data viz, info, video games, simulations, science, physics, all that stuff. This stuff is important because you need to visualize what's happening in the real world. Artificial intelligence cannot create something it has never seen or trained on before. That is why computer graphics is here to stay, and computer graphics programming is here to stay. So let's go on this journey together. This is Cuda Education. Thank you guys for watching. Have a great day. Have confidence and motivation in all the things that you do. Even if people don't believe in you, you have to believe in yourself. Okay? And I don't care who has a problem with that and who wants to complain and fuss and fight about you doing what you want to do. All right? Thank you guys for watching. Have a great day. Bye.